Welcome to lecture 7 on measure and integration. If you recall, in the previous lecture, we had started looking at the countably additive set functions on intervals, and we proved some properties of such countably additive set functions. We will recall that the theorem that we were proving and then continue the proof, and if time permits, we look at a characterizations of countably additive set functions defined on algebras in the later part of the lecture. So, let us just recall what we were proving in the last lecture. We were trying to show that if mu is a finitely additive set function defined on the collection of all left open right closed intervals, which was denoted by I tilde, if such a finitely additive set function is given with a property that mu of any finite interval is finite. So, mu of left open right closed interval a b is finite for every a and b. Then we wanted to characterize such countable additive properties of such functions and related to a class of functions on the real line. So, the claim of the theorem is that then there exists a monotonically increasing function f from R to R, such that the value mu of the left open right closed interval a b is given by f b minus f of a for every a and b belonging to R. So, we want to show that given a finitely additive set function on the class of all left open right closed intervals, it must arise from a monotonically increasing right continuous function f with the relation that the value mu of a b is given by the difference f b minus f of a. And in addition, if mu is here mu was only finitely additive, if we assume mu is countably additive, then f this function f can be selected to be right continuous. So, let us just recall how did we define this function. We looked at the function f defined by f at a point x is defined as the measure mu of the interval 0 to x if x is bigger than 0, and it is 0 if x is equal to 0, and is minus mu of x to 0 closed at 0 if x is less than 0. So, this was the definition of the function f, and we proved the property that this function f indeed is monotonically increasing. And for that, if you recall, we use the fact that f is the measure mu mu is a is a finitely additive set function. So, in next if we assume that mu is countably additive, we wanted to show that this function f is right continuous at every point x in R. And we had started looking at the proof when x is bigger than or equal to 0. So, we had proved that for x bigger any point x bigger than or equal to 0, f is right continuous at the point x is equal to 0. So, today we will start with proving the other part remaining part of the proof, namely if x is less than 0, then also f is right continuous at x. So, let us look at the proof. So, we want to show f is right continuous at a point x where x is less than 0. So, here is the point 0 and here is x. So, to show right continuity at the point x, let us take, so let x n belong to R. So, let us take points x n, a sequence in R, say that x n decreases to x. That means, x n is converging, all the x n's are on the right side of x and is converging to x. So, because all the points x n's are on the right side of, so here may be x n, x 1, here may be x 2 and so on. So, after some stage x n has to cross over the point 0, the value 0. So, what we are saying is without loss of generality assume that all the x n's are bigger than 0 for every n, because x n is going to converge to x and x is less than 0. So, at some stage it has to cross over. So, analyzing, we can start analyzing the sequence from that point onwards, or one writes this as, without loss of generality, the proof is not changed if we assume x n is less than 0 for every n. So, here is the situation, here is the point x, here is the point 0 and here is the point x 1. So, now let us look at, so here is x 2 and so on. So, let us observe that the interval left open right close 0 can be written as x 2 x 1 union x 1 to 0. So, I can write this as from this point to x 1 and from this point onwards to this one. And now, this interval x to x 1 I am going to split further into a union of intervals. So, my claim is that this x to x 1 is same as x 1 to x 2 union x 2 to x 3 union x 3 to x 4 and so on. So, we are going to claim is that this is same as x n plus 1 comma x n left open right close union n n equal to 0 to infinity union x 1 0. So, the interval x to x 1, this part we are splitting it into left open right close, left open right close and so on. And because this is true, this is equality, because x n is decreasing to x. So, at any point here in between, if I take from any point in between x and x 1, then that stage has to be crossed over by some x n. So, that point will belong here. So, this the interval x to x 1 is a union of the intervals left open x n plus 1 to closed x n equal to 0 to infinity. So, and also observe that these intervals are all disjoint. So, these are all disjoint intervals. So, I can write mu of using countable additive property of the set function. I can write this is equal to summation n equal to 0 to infinity mu of x n plus 1 x n plus mu of x 1 to 0. So, here we have used the fact that mu countably additive implies this property is true. And now, this right hand side is a sequence of non-negative real numbers, possibly extended real numbers. So, I can write this as limit k going to infinity sigma n equal to 0 to k mu of x n plus 1 x n plus mu of x 1 to 0, close here 0. So, now we will write everything in terms of f. So, by definition mu of x to 0 is minus f of x is equal to limit k going to infinity summation n equal to 0 to k, and this is nothing but f of x n minus f of x n plus 1 plus f of x 1 to 0. So, that is in fact minus f of x 1. So, now let us note what is this. So, this is a limit k going to infinity, and what is this sum? This is, it starts with n equal to 0 will give you x 0, that is not. So, let us so there was a mistake here. I should have written as union from n equal to 1, because it is 1 to 2, right, 1 to 2 and so on. So, that was the mistake here. So, this sum is from n equal to 1 to n equal to 1 to n equal to 1 to k. So, what is this sum? So, n equal to 1. So, that gives you f of x 1 minus f of x 2 plus f of x 2 minus f of x 3 and so on, plus f of x n equal to k. So, that is x k minus f of x k plus 1. And now, so that is this part, this sum, and minus f of x 1. So, now we observe that in this x 1, x 2, x 2, these will cancel out, and what is left with this is equal to f of x 1 minus f of x k plus 1 minus f of x 1. And now, in this equation, so this cancels with this. So, minus f of x, oh sorry, there is a limit outside. So, limit of this k going to infinity. So, what we get is f of x is equal to, so this gives us that f of x is equal to limit k going to infinity of f of x k plus 1, and that proves the fact that f is right continuous at x in the case when x was less than 0. So, hence f is right continuous for every x. So, this proves the theorem that if mu on the class of all left open right closed intervals is a measure, is countably additive with the property that mu of a b is equal mu of a b is finite for every a b in R, then this is implies there exists a function f which is monotonically increasing, which is right continuous. So, monotonically increasing right continuous such that mu of a b is equal to f b minus f of a. So, this is says, so what we have shown is that to every countably additive set function mu on left open right closed intervals, you can associate a monotonically increasing right continuous function. And we will next show. So, this is proved. This completes the proof of the fact that to every monotonically increasing right continuous function, we can associate a to every countably additive set function on the class of intervals, we can associate a monotonically increasing right continuous function with this property. In fact, the converse of this statement also holds. So, what will be the converse of such a statement? The converse of such a statement would be that if you are given a monotonically increasing right continuous function f, then we can define a set function mu on left open right closed intervals in such a way that this equation is satisfied, this relation is satisfied. So, that will prove that the only way monotonically only way we can construct countably additive set functions on the class of intervals is via monotonically increasing right continuous functions. So, the converse part of the theorem says the following: let f be a monotonically increasing function from R to R. So, define mu f a set function from the class of all left open right closed intervals as follows. For any two real numbers a and b, we want to define what is mu f of the closed left open right closed intervals a b. So, because this is the property has to be satisfied by f. So, that itself gives us the defining property of the set function mu. So, mu f of the left open right closed interval is defined as the difference f b minus f of a for all real numbers a and b. And now, the question comes, what happens if b is equal to plus infinity or a is equal to minus infinity or both of them. So, in that case we write this as for mu f of the infinite interval minus infinity to b. So, it is open on the left side and closed on the right side b. So, it is a left open right closed interval on the real line. So, what we do is we take the definition as f b minus f of minus x, x going to infinity. So, as x goes to infinity, minus x will go to minus infinity. So, we are using defining it via limits. So, look at the interval minus x to b left open. So, that is the value of the mu of f, and then take the limit of that as x goes to infinity. So, this is the definition of mu f of minus infinity to b, and similarly, if it is on the right side. So, if a to infinity, so what we define as take the interval a to closed x. So, then the value of that will be f of x minus f of a, and now take the limit of that as x goes to infinity. So, for the infinite interval unbounded on the right side, left open right closed. So, a to infinity is defined as limit x going to infinity f of x minus f of a, and if it is the whole real line, then we define mu of f of the whole real line to be limit x going to infinity of f of x minus f of minus x. So, look at the interval minus x to x and let both sides go to infinity. So, this is the way we define mu of f. And now, note that this is a generalization of the length function. If f is the identity function, namely f of x is equal to x, that is a monotonically increasing function, then this is nothing but b minus a. So, mu of a b is nothing but b minus a. So, this mu f is nothing but the length function when f is a monotonically increasing function. And one can write down a proof of this on the lines of when we proved that the length function is countably additive. So, on the same lines one can write down the proof of the fact that this set function mu f is also countably additive. One can wonder where one will be using the fact that f is right continuous. Okay. So, the fact where we will be using the right continuity of this f to prove that it is monotonically increasing, to prove that mu f is countably additive. So, this f is monotonically increasing, we can define this mu f is finitely additive, but to prove countable additive we need f to be a right continuous function. So, if f is right continuous, then one can write down a proof similar to that of the case of the length function. One uses the fact right continuity because one has to deal with the intervals which are left open and right closed. So, we suggest that if you are keen to know a proof of this, you better write a proof yourself, trying to see that the steps given for the proof of the length function is countable additive can be suitably modified to do this. So, we leave it as a exercise, and if you feel it is too tough an exercise, let us assume this and go ahead. So, mu f is a finitely additive sets function, and using if f is right continuous, one proves that mu f is also countably additive. So, this gives us this function mu f is called the set function induced by the increasing function f. So, this gives us a complete characterization of non-trivial countably additive set functions. Why non-trivial? Because we are looking at mu of the left open right closed interval a b to be finite in terms of functions which are monotonically increasing and right continuous. So, in some sense there is a correspondence between measures on the class of all intervals and monotonically increasing right continuous functions. In case that countably additive set function mu has the property that mu of the whole real line is finite, then one can select this monotonically increasing function to be mu of minus infinity to x, because then this is defined we do not have to restrict the fact that mu of a b is finite. That will be true anyway, because this is finite. So, a more canonical choice for the monotonically increasing right function, monotonically increasing right continuous function is mu of minus infinity to x, when mu of the whole space R is finite. So, in that case, this function f is called the distribution function on R, and this plays a role in the theory of probability, where the monotonically increasing right continuous functions are studied via what are called probability distributions. We will not go into that. So, we will just make a note of it in case we have finite condition that mu of R is finite. We will take mu f of x to be this function. So, this proves so we have characterized all countably additive set functions on the class of all intervals. The aim what we shall do now next is the following. We will study what are called set functions on a general class of sets called algebras, where so let us start with looking at an algebra of subsets of a set x, and mu a set function defined on this algebra taking non-negative real values. So, taking values in 0 to infinity. Then we want to show that the following holds, that if mu is finitely additive and mu of the set B is finite, okay, for a set B in the algebra A, then mu of the difference B minus A is equal to mu B minus mu of A, whenever A is in the algebra and A is a subset of B. So, what we are saying is the following. So, let us take two sets A and B belonging to the algebra A, and we are given, of course, A is a subset of B and mu of B is finite. So, here is the set B and A is a part of it. So, this B, so that is A. So, this part is A. So, we can write B as A union B minus A. So, this is the part B minus A, right. And note that A and B minus A both are disjoint sets. So, B is written as a finite union, in fact, union of the two sets A and B minus A, and they are pairwise disjoint, and mu finitely additive implies that mu of B is equal to mu of A plus mu of B minus A. And now, let us note that this all are real numbers. Mu of B is a real number because it is finite. Mu of A is a real number because A is a subset of B. So, that is and mu of A will be less than or equal to mu of B, that is finite. Okay. So, that is so these are all this is a equation in real numbers anyway. That is not really important here, but note that all are non-negative quantities. So, that implies that mu of B is bigger than or equal to mu of A. That is one thing that we observe, that because this is non-negative. So, this also implies that mu of A is less than or equal to mu of B, which is finite, right. So, that implies mu of A is finite. So, in this equation now I can say all are real numbers. So, I can manipulate this as equation in real numbers. So, this equation implies that if I take it on the other side. So, mu of B minus mu of A is equal to mu of B minus A. So, that is what we wanted to prove, and note here we have used the fact that mu of B is finite, and hence mu of every subset of it is finite whenever that set is in the algebra, right. So, we can manipulate this as a equation only when they are real numbers. If they are equal to plus infinity or minus plus infinity at any one of them, then I cannot transpose them on the other side and write this equation. So, we have used the fact that mu is finitely additive and mu of B is finite. That implies for every subset A of B, which is in the algebra, mu of A is also finite and mu of B minus A is equal to mu of B minus mu of A. And in particular, supposing I take B equal to A, so this gives mu of empty set is equal to 0. So, in particular mu of empty set is 0 if mu is finitely additive and mu for at least one set B is finite. So, these are consequences of a set function being finitely additive. So, what we are trying to show is if a set function is finitely additive, what are the possible consequences? We showed finite additivity implies monotone, right, and if B is finite, then I can interchange and write mu of B minus A to be equal to this. Finite additive plus mu of at least one set is finite implies mu of phi is equal to 0.